Welcome to our next entry in this engineering math series focusing on probability. For the past couple of videos, we've been dealing with probability distributions and kind of defining the properties, expected value and variance, and kind of how they work. We talked about cumulative distributions, but we restricted ourselves to a discussion involving only discrete random variables. And if you recall, a discrete random variable is basically one in which I have a value of singular numbers that represent my random variable. So in this case, my random variable x could have a value of 0, a 1, a 2, or a 3, and then the fx represents the probability associated with each of those values. So kind of think of this as it's kind of like a step function almost as you start to kind of work with these. Okay, and then to find probabilities of specific values or probabilities of, say, 1 and 2 together, you would add the probability of this bar to the probability of this bar. It was always a summation kind of operation. All right, and that's one of the characteristics of these probability mass functions, which are used to describe discrete random variables. In this video, we're going to change it up a little bit and go look at continuous random variables. And so instead of being this step function like we had with discrete, now it's going to be kind of this continuous curve. Okay, so I'm going to be able to, where before I was restricted to singular values, in this case 0, 1, 2, and 3, now I can have ranges of values and I can have decimal values associated with these. And so these become continuous functions, if you will. Okay, and so as you might expect, if you remember back in calculus, we could do operations on functions in which I would take a function f of x that looks something kind of like this, and the first thing that they taught you how to do is you would go back and you would break it in and do a rectangle rule or a trapezoidal rule or something to discretize that into these lump little pieces. It's the same thought process. Okay, so instead of doing a summation on the discrete, now I'm going to be doing an integral, okay, on these operations, and I'm going to be looking for integrals of this function. Okay, which means that if you remember from calculus, anytime you integrate a function, you're finding the area underneath that function, and then I'll set boundaries of the two ranges of values that I want. An upper limit of lowercase b is pretty typical, and a lower limit of lowercase a is the other one. And so those become kind of our usual kind of methodology for what we're trying to do. Okay, now as you might expect, for continuous random variables, when we did the discrete stuff, we had some properties and things that we had to look at. Okay, so for continuous random variables, we're going to define a probability density function instead of the mass function because it's a continuous curve. Okay, and we're going to use that instead of the PMF. All right, so what we're doing is now we're looking for probabilities of ranges. Okay, so the probability of A being less than or equal to X, less than or equal to B is represented by the shaded area that you see on this curve. Again, this is my probability density function, and there are some requirements to setting this up that we have to make sure, and we'll talk about those. Okay, but once I get it set up right, then the probability of my random variable falling between those ranges becomes equal to the area of that. And so if you remember from calculus, all you're doing then is just the integral from b to a of fx dx, okay, where fx is that probability density function equation. Okay, and like I say, it's basically the area operation. Okay, back in the discretes, it was a sum of fx and dx kind of operation. So that's all we're doing is we're trading this integral between the range to a summation of, whatever values I'm wanting to include in the discrete. So it's pretty cool. It's not too hard. It's a little squirrely at first, but after you kind of get your head wrapped around it, it's not too shabby. Okay, all right, get my paper up here where we can see. Okay, so basically we can say that any function can be used as a PDF if it meets a certain set of criteria. All right, so the first one is that the function itself has to be positive. It has to be greater than 0 at all values. I can't ever go negative on this. So for all x on which the function is defined, it has to be greater than 0. Okay, and that was the same as what we had with the discretes, right? We had to have positive probabilities. Okay, the next one is that the integral from positive infinity to negative infinity, which is basically the entire domain of x, okay, is going to be the fx dx has to be equal to 1.0. And you've seen that one before, because before we said that it was the probability of our sample space had to be 1.0. So sample space is everything that we're considering. Positive infinity to negative infinity is everything that we're considering, okay? So these are the same properties that you had in discrete as the discretes, it's just they're written a little bit differently. All right, however, there is one big difference, and that's what I want to kind of emphasize here on this, okay? And that is that because our probabilities are now, based on integrals, as we saw here, okay, what happens if little a and little b are the same value? All right, well, what you've done is you've now defined basically a line under this curve, and there is no area for a line. And so for a singular numerical value, such as the probability of random variable x being equal to that some single value, is always 0 for a 0, or for a singular value. Okay, so that's kind of a subtle little trick. This is the exact opposite of what we did in discrete. In discrete, this is what we were calculating. Okay, but now that's the case. But it has a very important effect on continuous calculations, right? Before, we were worried about less than or equal to x, or greater than or equal to some value. We were worried about the greater thans and the equals, at least, at most, more than, all of those kind of problems. Now in continuous, I don't care anymore, right? That basically x being greater than or equal to a and less than or equal to b is probability of a less than x. Notice the equal is gone, and then less than b, the equal is gone. So I can move back and forth freely between these, because I know that for singular values, the probability is equal to 0, okay? Basically, equality, this equality has a 0 probability of happening exactly. We're looking for ranges in the mathematical operations that we're fixing to do. So, all right, so that kind of sets us up for some continuous effects. So let's give one a try and kind of see what we can come up with. All right, so what we have here is I've defined, a basic operation, and so I've plotted a PDF for this one, okay, or a function, if you will, that lives between 0 and 2, and it's a parabolic curve that has a constant k times x squared. Okay, and so this is my function that, based on some data that I've collected or whatever, this is what the line that fits that data the best. Okay, so what we have to do, the first step we have to do is we have to figure out what the PDF is going to be. And the way that we do that is we're going to play with this k factor, this scaling factor, if you will. All right, because again, the total area under my domain has to be 1.0 in order for my operations to be able to yield out probabilities. So this is a very, very important step that we're looking to do. All right, so we're going to take advantage of that second rule that we had, and I'm going to integrate over the domain, which really should be from positive infinity to negative infinity, but we know that from infinity to 2, and then from 0 to minus infinity, all of the integrations of all of this stuff, that guy is 0 and that guy is 0. So I can split that infinite integral into the range over which I'm working, because it's not defined anywhere else outside of that. Okay, so that's why you only see the limits from 2 to 0, not positive infinity to negative infinity. So with that being fx dx, we set that equal to 1.0. All I'm going to do is plug in the function that I want to fit to this curve. So I'm going to plug in kx squared, which was what we defined as the curve up here. And again, k is a constant we haven't figured out. And then I'm going to integrate that and set it equal to 1.0. So when I do that, just doing a lot of calculus involved in this, and this is kind of the nature of the beast. So say it's going to be k times x cubed over 3. I'm going to evaluate from x equals 2 to x equals 0, and all that has to be equal to 1.0. And then basically I'm going to do the final evaluation, and I'm going to solve for k. And so when I do that, k ends up being 3/8. Okay, so this is basically the scaling factor to create our PDF. So our PDF then on here is defined as follows. The function f of x is going to be 3/8 x squared on the interval of 0 less than or equal to x, less than or equal to 2, and 0 elsewhere. Okay, so that's the way that we define these continuous random variables. Okay, all right, so now that we've got that figured out, now we can go in and we can play all the probability games that we want. So the first one is, let's find the probability that x is between 1 and 1.5. Well, again, all we're doing is we're integrating. So if I set that as b and I set this as a, then this piece right here is my f of x, right? And so I just basically, it's now just a calculus problem to be able to solve for it. So I'll save you some of the, the actual calculus steps. If you're having issues with that, we'll get some videos up to help with that eventually, but hopefully basic integration is just power rule stuff. I'm going to assume that you know how to do that. Okay, so when we do that, and then I go through and I do the math on this, I'll find out that this integral between those ranges evaluates to 19 over 64, or is 0.297, about 29.7% on those. Okay, now, what do we do when I don't care about one of the bounds? So let's do the probability of x less than 1. Well, again, the original integral went from positive infinity to minus infinity. Okay, and so now we're going from 1 to minus infinity of my f of x dx function. That's how we start to kind of evaluate this. And so obviously from 0 to minus infinity, that falls in this range of 0, so that drops out. And then I'm left with from 1 to 0 as being a valid range for my problem of 3/8 x squared dx. And again, I can evaluate the math, watching the limits, that it's 1 here and 0 here now. And when I do that, I get the value of 1/8, okay, or 0.125. So you can do all sorts of calculations that look something like this. Okay, you can do it on the upper bound as well. Okay, so now I'm doing for x greater than 1.5. Okay, so we're going to set b as positive infinity and a as 1.5 on there, and I throw it into my integral, and away we go. So here's the infinity, here's the 1.5, f of x dx, plug it in and go. So just like we did before, because from 2 to infinity is in my undefined range up here, beyond 2, the only piece that contributes to the probability then is the portion that lives then between 2 and 1.5. This term will vanish, it goes away. Okay, so then it's from 2 to 1.5 of 3/8 x squared dx. Do the calculus, and you get 37/64, or 0.578 as our problem there. Like I say, if you want to pause the video and go through the math and make sure that it makes sense to you, that's fine. But I'm going to kind of keep on going in an effort to try to keep this video relatively short. So anyway, hope that makes sense to you. All right, so now that's the basics of how you work with these distributions. Let's go through and let's start looking at some of the specialized ones. There's a lot of very useful distributions in our calculations, okay, or in the realm of continuous distributions. The first one we're going to look at is what we call a uniform distribution, okay? And so we've got a uniform distribution, we'll look at a normal, which is a very common one, and we'll look at some of the others, some gamma functions, and some special cases of other types of continuous distributions, exponentials. I think a logarithmic will show up at some point, all those. But we're going to start off with keeping it fairly simple. And remember, for us, it's all about what do we assume about the data. So a uniform distribution has the characteristic that it is a constant function. It is some value that we don't know, okay, but it's the same value over my interval, okay, over the entire domain. So capital A is the lower bound, capital B is the upper bound, and all my probability lives between those two limits. And it's the exact same probability along that functional line. It's basically a horizontal line. So what we do then is we go back and to kind of show where it's at, this is what the function looks like as a PDF. Okay, so we're going to have our function of x with input parameters a and b, the capital A, capital B, lower limit, upper limit. Okay, and so between those limits, our value is 1 over b minus a. It will be the value of this function here, and then a less than or equal to x less than b, and then it's 0 everywhere else. So this is the uniform distribution definition. Now, let's talk about where this came from. Okay, as you might suspect, we're going to go back and we're going to play the area game, right? We know that the probability of the sample space, or the entire area of our diagram, has to equal 1.0. Right? Now, because this is a rectangle, I don't need to integrate, but I know that it's going to be this distance horizontally multiplied by the height of this because that's a rectangle, right? So base times height. So what I have is the height is fx, the base is b minus a, and we just said that that has to be equal to 1.0. So fx times b minus a is the area, equals 1.0. So I can solve for the fx value as being 1 over b minus a. That's where it comes from. Okay, so simply the area being set equal to 1. Okay, so once I have it, now we can actually start doing probability games. And like I say, the rectangular ones, the uniform distributions, are pretty simple to kind of grasp your head around as we look at that. So let's consider temperatures in a chemical process are said to be constant. Okay, well, the word constant means uniform distributed. All right, and it's going to be over the interval of minus 5 degrees, let's just say Fahrenheit, and Fahrenheit to plus 5 degrees Fahrenheit on there. And it's the same process, or same probability everywhere in between, okay? We're going to define the random variable x as being my temperature, okay? And so for our diagram, if we look at this to set up the PDF that we need to distribute this, we set b equal to plus 5, that's the upper limit, that's here, and a is equal to minus 5 is the lower limit, is the one that's right there. All right, so my PDF then is going to be the function, random variable x, limits of a and b. Okay, so 1 over b minus a becomes 1 over 5 minus a minus 5 becomes 1 over 10. So the intensity of this is 1/10. Okay, and a less than or equal to x less than b, and then it's 0 everywhere else. All right, and that should make sense, right? Because it's 10 units from here to here, so I need 1/10 height in order to make this box have an area of 1.0. Okay, so then once we have this defined, now you're in business. We go back and play the exact same game we did on the last examples. Okay, so if I want the probability that x is less than 0, I'm going to integrate from 0 upper bound to -5 lower bound. And again, we've chopped off the integrals from infinity to minus infinity, and I'm just dealing with what's in the domain that I'm looking at. Okay, so f of x dx, 0 to 5, 1/10 dx. You can do the calculus, and so obviously from 0 to -5 is half of this area, right, which is what the calculus proves. Okay, but that's the math that we would do to be able to do that. We could go through, we could do the upper and lower bounds are set, so here's my little a, here's my little b. We're going from positive 2.5 to minus 2.5. You probably see it already. It's 5 units this way. It was 10 wide, so this is going to be half again, but the math looks like this. Upper limit 2.5, bottom limit minus 2.5, f of x dx. Do the calculus, 1/10 is my function. Plug in, do the math, you get the half value, which is what you would expect. Okay, so uniforms, a lot of times you don't have to do the calculus because you can just kind of compute the area and take it as what fraction of the total area are we dealing with here. Okay, we can also go in and then do, greater than or equals, and again, it's the same evaluation. We don't care about those values. So here's my a, -3, my b is positive 4. You come through and do it. It's now 7/10. So the probability of falling in that range is 0.7. Super, super easy once you get this step figured out. All right, that's the hard part, is getting this guy calibrated so that the area under the entire curve ends up being equal to 1.0. And even that's not that difficult. So that's our uniform distribution. All right, now in discretes, we also talked about a couple of other properties. Okay, we have the cumulative distribution function, which is related to it. And then we also talked about expected value and variance for discrete probability functions. Cumulatives have them too. Okay, so we're going to stick with the same nomenclature that we had. Okay, and so to compute the cumulative of a random variable x, okay, this is basically the probability that my random variable is less than some singular value. Okay, and so all we do is we basically, to find that area less than this parameter x, is I integrate from that x all the way down to minus infinity, because this is a leftward bound problem, right? That if I have an x that's here, we're looking to calculate that area. That's the cumulative. Okay, and so f of y dy, and we can integrate. And so as you might expect, if I started out at some lower bound of a on this, the cumulative will even though I may be bell-shaped here, this isn't even uniform, this is more normally distributed, bell-shaped, it will continuously build up, and then eventually it will reach a 1.0, at which point it will stay constant all the way out to positive infinity. Okay, that's the definition of a cumulative. From the starting point to negative infinity is 0, because there's nothing less than my lower bound limit. And so that's kind of what we're trying to show here. Okay, so here are some of the propositions that we have. Okay, so just like you might expect, the probability of a random variable x being greater than some value, say little a, is basically going to be 1 minus the cumulative evaluated at that point, right? Because again, what we're looking for is we're trying to do 1 minus the probability of x less than or equal to a. Right? And that was this was the same game that we played back in the discrete. It was flipping it and playing with the complement. Well, again, we know that this definition of this term is a cumulative function or a cumulative operator. Okay, so we can do that. We can go through and find the probability between two ranges, a less than or equal to x less than or b, is the cumulative of b minus the lower bound. So what we've done, if we come in and say that b was here, we have found that area, okay, and from it we have subtracted, same curve, the lower bound, okay, and what's left then is, here's my curve, here's my A, here's my B, that's my area. We have now found that area by doing it. So the cumulative of this minus the cumulative of that will get me an area between two limits. And that's all that we've done. Okay, so that's kind of the sneaky little trick on this. And if you understand this, and you're in great shape going forward into confidence intervals and being able to draw these pictures and to be able to figure out what those operations are and what the pieces of the puzzle are, so to say. Okay, all right, and now if I have a cumulative function defined, or capital F of x, I can always get back the PDF of this. This is my PDF, okay, by simply taking the first derivative of that function. Okay, and because in order to get this, we integrated, all right? So if I take the first derivative, I should get back f of x. And so that can be useful at times, I guess, from a theoretical standpoint. In practice, it doesn't happen that way very often, but we can work with it. You can move back and forth between it. To go from here to here, I integrate, and to go from here to here, I differentiate. So you can kind of undo all those operations. No major surprises, hopefully. Okay, all right. So now let's get into the meat of this, okay? One of the factors that we need to know is the expected value. Okay, so again, for a population, we're going to use the character mu to represent the expected value of a continuous function. Okay, and so before, if you remember back in the discrete operators, it was the sum of all x times the probability of x. And then we had the functional form, which was, where instead of being x, it was a function of x. That hx equation times the probability of x summed over all x would be the discrete operators. Well, as you might imagine, all I do is I replace this summation symbol with an integral. And all x means from positive infinity to minus infinity. So we're going to take positive infinity to minus infinity of x, that's this piece, multiplied by f of x, that's this piece, and I'm going to integrate it with respect to x. There it is. That's the expected value of the variable x for a given distribution. For e, as the expected value of our h of x on this, then all I do is I change this x for an h of x, and then multiply that by our f of x, and then we get our dx. Now, obviously, this operation can get a little ugly if this is pretty complex and this is complex too, but again, it's a math exercise at that point. The statistics and the engineering math behind it are very, very simple and very, very basic. Okay, all right. Okay, so let's give one a try and kind of see what we can kind of start to do with this, all right? So what I have is I have kind of a propane sales yard, if you will. If you ever watched King of the Hill, propane and propane accessories, a pretty cool, fun cartoon from many years ago. All right, but so for propane, we're going to define a random variable x as the demand. Okay, and so we're going to plot the weekly demand for propane in thousands of gallons. Okay, and so based off of historical data, they have collected that the amount of gallons that are left, if they were to plot all of the points on this and then fit a curve to it, some function f of x, which is equal to 2 times 1 minus 1 over x squared, and it lives between 1,000 gallons and 2,000 gallons on any given week. Okay, and then it's 0 anytime you're less than 1,000 or greater than 2,000. Okay, so it's not uniform, it's not normal, it's just a continuous function that defines this demand curve. Okay, so the first thing that we always have to do in all of these continuous problems is determine, do we have a valid PDF? All right, and so the way that we test that is we come back to that integral over the entire domain from infinity to minus infinity of f of x dx equal to 1.0. All right, so now if we look, notice that our curve only lives on the interval from 1,000 to 2,000 or from 1 to 2. I'm going to write everything as 1 and 2, but recognize that everything is implying thousands of gallons here. Okay, so all I do is we go from 1 to minus infinity, 0, 2 to 1 of our function, dx, plus infinity to 2 of 0, because anything to the left of 1 is 0 and anything to the right of 2 is 0 for us to do there. So then again, just like we did before, it's a calculus problem. Okay, and so 2 times 1 minus 1 over x squared dx. Okay, recognize that this term is x to the minus 2, and so when I integrate that, it becomes x to the minus 1. Okay, so 2x plus 2 times 1 over x, evaluated at x equals 2 and x equals 1. If I plug those limits into here, I get the math that this is, 2 times 2 plus 2 times a half minus 2 times 1 plus 2 times 1 over 1 becomes 5 minus 4, which is 1. And the fact that that's 1 tells me this is a valid PDF. So with that, now I can jump straight into the function. Now I can start playing all sorts of games. So suppose we want to know the cumulative. Okay, so to create a cumulative function for this, all right, so we're going to do the f of x for my cumulative function of the variable x. And I'm going to integrate from x to minus infinity of my PDF, f of y dy. And so again, from x to 1 is defined, from 1 to minus infinity is not. It's a 0, so I didn't even write it this time. Okay, times my function dy on the interval 1 less than or equal to x less than 2. And so this becomes 2 times y plus 1 over y evaluated from x to 1. And so now we can just kind of do our algebra on this case, and it becomes 2 times x plus 1 over x minus 2 becomes the functional value of x. Okay, and that's from 1 less than or equal to x less than or equal to 2. Now, one change that happens is whenever I go beyond 2, remember, this becomes 1.0. Okay, so before on the PDF it was 0 when we were over 2, but on the cumulative it goes to 1.0. And so that's the CDF upper limit value, or that it stays at this value for all values above 2 is the definition of it. Okay, all right? Okay, now let's take that function and then let's go in and let's see if we can figure out what the expected value is. So the expected value of x, okay, as you might expect, is we're going to integrate from minus infinity. Oops, that should be, I got this completely backwards. Let's put a positive here and a minus on the bottom. Okay, It's not going to matter. We're going to chop all those off anyway. But so x times f of x dx is the equation. Okay, so we're going to convert our limits to 2 and 1 for the same reasons. There's nothing above, nothing below. So the limit where it exists is 2 to 1 of x times 2 times 1 minus 1 over x squared dx. And you can do the calculus. And what you'll find is that this expected value of the random variable x is going to be 1,614 gallons, or 1.16 times 1,000 gallons. That's what you expect to have in the tank demand in any given week, 1.614. Okay, now to find Vx, remember that we can always do the shortcut equation, expected value of x squared minus the expected value of x, that guy squared. So I have this piece already. So if we come and compute the second piece, I can get the variance very easily. All right, and so that's what we do on the next line. We're going to do the expected value of x squared, again, from minus, wow, I did it again. Minus to, from positive to minus on there. And now we're doing x squared, that's my function, times fx dx. And then we're going to integrate, do the math. And if you carry through all of this and don't make a mistake like I did the first time, we'll have 2.667 becomes the expected value of x squared. Okay, and so then the variance on this data curve then is the expected value of our x squared calculation minus the expected value of x quantity squared. Okay, so you got to kind of watch where the parentheses are on this. So I take the 2.667 that I had here, and I subtract off the 1.614 I have here, and then I square that piece. Okay, and if I do that, my variance is now 0.617, okay, or a little less than 62 gallons of variance. So it's a pretty consistent operation that they have on this particular curve. Okay, so those are some basic operators on how you find expected value and how you start to find the variance. Okay, now let's go to another step and kind of ramp it up a little bit. Okay, suppose that we have 1.5 thousand gallons or 1,500 gallons in stock. Okay, what we can do is we can go, how much total fuel is expected to be left at the end of the week? Okay, and again, we're going to assume that there are no refills, that the truck comes on Monday and it doesn't come again until Monday. All right, and so what we want to look at then is, we can say, let's define h of x as my function, because x is the demand, be the amount of fuel left in the tank. All right, so it's a function of the demand. Well, this demand curve is a little bit different, right? Because if I'm less than, if my demand is less than 1,500 gallons, I have a positive value. So if the bottom value is 1, I would have a limit of 500 gallons left, right? And then if I go all the way out to 1.5, at 1.5, I now have 0 left, okay? And so my function is, it's a linear function here on x, so that's why that's a straight line. But notice that it's 0 here, right? Because this curve on that function wants to keep going negative, but I can't have a negative quantity in there, right? And somebody's not driving up and putting fuel in my tank for me, all right? So at this point, we have to follow this curve. So this becomes kind of a max operator, if you remember those, okay? And so it's going to be the maximum value of either 1.5 minus x or 0. Okay, so if I'm over on this side, the max is always the value on this line. If I'm over on this side, instead of being here, my max is always 0. And so that's the way that we can define this. Okay, and so what that means then is that this max operator, I can define h of x as being 1.5 minus x when when x is between 1 and 1.5. And it's 0 when I'm between 1.5 and 2. Because if I have a demand out here, I've drained the tank and it goes negative. So the expected value of the amount that's left, this h of x function, again, we're going to integrate from positive infinity to minus infinity. Look at that, I got it right that time. Okay, it's going to be h of x times f of x dx. Okay, and then if I chop off all of the pieces, the only piece that survives is going to be 1.5 to 1, right? Because the integral from 2 to 1.5 is going to have a 0 for h of x multiplied by f of x dx. And so that piece is going to vanish, because of the 0 that's over here. All right, so the only piece that survives is this integral from 1.5 to 1. And so if I do that, my h of x function and that interval is 1.5 minus x. I'm going to multiply it by my density equation, 2 times 1 over 1 minus x squared dx. And I'm going to integrate, and again, just to save you the time, you'll have to do some algebra to FOIL this thing and then integrate that guy and substitute in your limits of 1.51. You get a value of 0.061. All right, so the estimated amount of fuel that's left at the end of the week on this, if I stock 1.5 thousand gallons, is 61 gallons remaining. And so that's not a bad little amount. I mean, as a store owner, you want to you like to fully sell everything that you have. So there's always going to be a little bit left. So 61 gallons is good. And then on the weeks where you get a lot of traffic, that does drain you out, well, that's okay. Okay, so that's kind of what we're looking at, kind of working on this. So anyway, that's kind of some operations that you can do with some other little twisty pieces in this thing. This h of x function is kind of interesting. But all you're doing, again, and when dealing with these cumulatives, whether it's a uniform or just a generic cumulative equation trying to do expected values, is you're playing with the limits of integration. So for expected values, I'm going from infinity to minus infinity. For probabilities, I go from the upper limit to the lower limit of the range of values that you're trying to compute the probability for. But the rest of it is exactly the same. Okay, so it's not too bad. Hopefully that made sense to you. We'll stop here now, and in the coming videos, we'll start talking about some of the other different types of continuous distributions and their characteristics. And we're going to, the next one up is going to be the normal distribution, and that's a very, very useful one in engineering, and I'm going to show you some tricks on that. So tune into the video for that one when you get a chance. I'll greatly appreciate it. As always, leave us some comments down below, toss us a like on the channel or on the video, and if you wish to subscribe, please do so. And we'll look forward to seeing you all back here next time. Have a great evening. Happy engineering.